Hi, everybody. I'm Nimbus. Thank you for coming to a talk on a rather niche subject at 4 p.m. on a Sunday. Go, everyone, here. So my name's Nimbus. I work at Bloomberg on Spark platform infrastructure, generally helping to provide and make life easier for data scientists and engineers who are trying to get various workloads done in Spark and make their lives easier. So what I'm going to be talking about are data pipelines generally. And this is a very broad overview of a simple data pipeline where you take in some sources of data, you run some process over it in order to get some output. And this is at a very zoomed out. You can imagine zooming into this process, and there might be all sorts of other things. But one thing to notice about these things is it's a DAG, or a directed acyclic graph. So within the process, there might be like a sub-DAG there going on. When you're developing this sort of thing, if you are doing this in a notebook, it's pretty straightforward. You can cache things in Spark. You can run some code. You can see how it does, and if it doesn't do what you want, you can change it and rerun it. And in the notebook experience in Spark is very good. You can cache things appropriately. You can reuse them. You don't have to start all the way from the beginning each time. But if you're not, there's a certain kind of like complexity of a project once you get beyond the kind of simple prototyping, just to check if you have like a one-page kind of notebook thing and it works for you, that's great. But if you start wanting to check your code into a repository, have a whole project, have compile time checks, then you're in the situation where you have a library. And if you run some code that depends on that library and you realize you need to make changes to that, then you have to worry about this cycle here, where when you make a code change in your library, you have to redeploy your jar. You have to restart your Spark application, whether it be like a notebook thing where you depend on that jar, or some kind of submission to a cluster. And then you have to wait for it to run. So if, by contrast with like a notebook where you're making changes there and not having to reload jars, you do have to start from the beginning when you are trying to reload a new jar with some changes to your code. And each time you make a change to your library and you want to see what it does, you have to wait for this cycle. And this can, obviously, these can sometimes be slower to deploy a jar or to start a submission. But generally, most of the time comes in the execution of like the actual distributed processing. If this is kind of very small, just a couple minutes, then it's not so bad. But it can get large depending on what you're trying to do. So when you go and run your code on your data pipeline, you kind of cross your fingers, hope it works, and then sometimes something like this will happen. You have some strange error. Or maybe you don't have some strange error, but your output is coming not at what you expected with no error, but still not the answer you're hoping for. But when something like this happens, it's like in the regular course of programming most typical things, I think a lot of people do something called like monkey patching, or just just hitting something until it works, or some kind of percussive maintenance. And it's not, that's a reasonable thing to do. It's just that's part of the debugging process, is to fiddle with things, rerun it, and see if it changes anything. There's sort of not a great way around some of these things. Obviously, it makes sense to test as much as you can ahead of time on small data sets and see that your code is logically correct on a small amount of input. But there's this, even if you do your best practices, you will get into situations where you're running into something that fails on 1 out of 10,000 things. Then those can be hard to catch ahead of time. And I think if you ask around, data engineers, data scientists, where do they spend a lot of time kind of dealing with it? And it's often dealing with problems that arise when you plug in the full data set and dealing with those mysterious issues. So for that reason, what people will go and do on their own is to split their code up into stages. So what was just one simple process that goes from start to finish, because if you're dealing with an issue kind of in the second half of that, and it takes a while for it to run before you hit your issue, people will go and take their code, split it up into stages. So where before we had just one single process, now we have stage 1 and stage 2. So stage 1, it has its own main. We read from some source, and then we run some various processes over it, and then we save some output. And stage 2 is a separate main where we load the stage 1 path from the previously saved output from stage 1. We run some process on it, and then we save some output or compute some output. So why do people do this? They do this to save time, because if you're running into some kind of difficult issue in this area, and say stage 1 is, it's at least, it's simple and appears to be correct, but it might be time consuming. It might be something where you take a few data sets, you join them together to produce some kind of denormalized output. It might be working just fine, but you don't want to run it every time if you're trying to figure out something here. So you'd rather just run it once, save your output, and then you can fiddle with this as much as you like in order to get your program working correctly. But this kind of thing is, we're creating a couple of new problems by trying to rearrange things in order to save ourselves time debugging. Some of the issues we create are, where before we could just had a single entry point. We could just trigger one thing and it would do the whole thing. Now we have 2 entry points. So we would have to, if we wanted a single entry point, we'd have to have another thing that maybe we have 3 entry points now. We have one that calls stage 1, we have one that calls stage 2, and then we could have another that calls stage 1 and then stage 2. And maybe use that for when we want it. Use any of them depending on when you want it. If for some reason, you thought that stage 1 was correct at first, but then it's at least running without error, but then you find something in stage 2 that looks amiss, and you realize you need to change something in stage 1. And if you do that, what you need to do is you have to run stage 1 and either override the output or save it to a new output and make sure stage 2 is now picking up from that new output. And those certainly aren't difficult things to do, but it's just several simple things that you have to remember, and that is not going to happen automatically unless you make it. So moving your code into kind of a multi-stage setup when it really could have been easier to express as a single stage creates some issues like that. And also, if you say you have multiple people working on kind of an overlapping project, or multiple people contributing to the same project, but just kind of working on different parts of it, running different sections at once. Often, because some of these things are very large and you don't want everyone to save their own copy of these things, people might share intermediate results, so that maybe you have your initial thing writing to kind of a large amount, and kind of you clean it up and save it in one place, and then you have multiple people kind of working off of those. If you realize those need to change for whatever reason, then it's thorny to deal with. It can be thorny to deal with that. And then you also have to worry with if some people are ever overwriting things and other people are kind of not, that can create some issues. So what would be nice is if some of this stuff we didn't have to worry about handcrafting this in a custom way every time. If it just kind of did it itself, that would be nice. And so what would it look like if if these things did them, if it did it by itself. It might look something like this, where we have these dotted lines are kind of paths that may or may not be executed in a given execution. So now we're expressing this as just a single entry point. We run stage 1 on some source, and then we get stage 1 out, and then we run stage 2 on stage 1 out in order to get some output. So now we have a single entry point. It does the whole thing, but we also added a little dot checkpoint on stage 1 because we want to avoid redundant computation. If we have already run stage 1, we would rather just use it. And so ideally, the first time we run this, we would start with a source. We would run stage 1. We would save its output, and we would also send its output to stage 2, which then runs and then does the output. So this is like a typical full run of the whole thing, plus another step where we save the output of stage 1 somewhere. However, the second time we run this, since we already have stage 1 output saved, we just want to use that, feed it into stage 2, run that into the output. So stage 1 doesn't execute if we already have this around. And then, if for whatever reason, stage 1 changed, we had a new stage that's logically different, we really want to disregard the old output because we've just changed this section. We don't want to use what we saved before because now it's kind of invalidated. So we want to save a new output and also send the new output along to stage 2. What are the things that we need in order to do this? So one of the key things is we need, since we're saving this somewhere and loading it later, we need to save it to some path. And so we need some way of generating a path automatically. And that path, we want it to stay the same if we are avoiding redundant computation. We've already made that computation, and we just want to resume from it. And it should be different if, for whatever reason, there's a change in logic. We definitely want to compute something freshly and ignore what might be saved already. So if the path changes when that happens, then it's good. So now in Spark, so now this also applies. How do we define RDDs? How can we find some kind of identity for these things? And this also applies to data frames and data sets. So for a given RDD, we have some set of dependencies on other RDDs. And the number of dependencies depends on what kind of RDD it is. It could, in fact, be 0 in the case of like a text file or some kind of basically a source RDD where you just specify a path and there's no prior RDD. It's just, it just comes into existence with no dependencies on RDDs. And there's some kind of logic we apply in order to produce the result. And this is also how RDDs have resilient in their name, because you can run this again. If for some reason you lose part of the result, you can just rerun, and you still have the dependencies and the logic, you can just rerun those. So part of how Spark works is it relies on this, that you should, as long as you have the dependencies and the logic, it doesn't matter. If you already have the result, great, but if you don't, you can recompute it and it will be consistent. So for a concrete example, say we have just the natural numbers in an RDD, and we produce a new RDD by mapping a function over this one, say double every number, and then the result will be 2, 4, 6, 8, 10, and so on. So if for some reason we forgot about this, that's OK. We can recompute it. So really, what determines the identity of this is the dependencies and the logic. If we have these two things, we kind of know what this could be. And if these things are the same, then this will be the same. So we can encode this in a hash, basically. We can, if a result is the logic applied to dependencies, we can say the signature of that result is the signature of the dependencies, or the combined signatures of the dependencies, plus a hash of the logic, and then kind of combined and hashed together. Just so that, and the point is, if we run this in a new execution and things come up the same, and they have the same signatures, we know that we've already been here before. We have kind of made this computation before, and we can resume it. And if we come up with something different, we know that this is something fresh. So with a more concrete example, so we have, say, some RDD1. We map a function f over it to produce RDD2. The signature of RDD2 should be equal to the combined hash of the signature of RDD1 and a hash of the function f. And for something where it doesn't have any dependencies on prior RDDs, like some kind of source RDD, if you just load a text file from some URI, that's just a string, then you can just make a really simple hash of a string that is basically just the URI plus some kind of constant that determines what kind of source type it is. Like you might have a different one for Parquet files, and if you're loading something as a Parquet file versus a text file or versus an object file. Do you have a question?
Yeah. How do you deal with dynamic configuration?
Dynamic configuration? What do you mean?
If my configuration comes from a database.
Oh,
so that URI will essentially be driven by the database.
So if you're talking if you have a path and the underlying data changes, or so one of the things, so I'll be kind of getting to this, but yeah, it doesn't know if it's basically considering the identity of something as just the path. So if the underlying data changes, it's not going to pick those up. But in many cases, when people make these stages or split their pipeline up into stages, they're also missing out on this. So if you go and save some intermediate results, obviously if the source changes out from under it, you're not going to pass those along unless you explicitly replace them. So this is not designed to handle all those cases. And in many cases, you actually don't necessarily want to pass along every little update all the time. In cases where this is mainly to in the process of development and debugging, in order to produce a correct solution, you are typically okay with using a particular snapshot of the data at some time. And for example, it often makes sense to compose and specify your pipeline as something that you could run again later with the same arguments in order to produce the same answer. And as an example of that, what is something people will do to kind of ensure kind of validity, and so that you could run it again to get the same answer, you might set a high watermark, for example. If you specify as arguments to your pipeline, and part of the logic is use all data up to this point in order to produce some kind of result that is valid at that time, then you can even run that again later, even if there's new data, and you should get the same answer. And it's sometimes people sometimes recommend doing in that form, because you don't have to worry about starting it at different times and getting different answers. Okay. So now I kind of just offhandedly mentioned, oh yeah, just hash a function, no big deal, right? But it kind of is a big deal. There's not really a built-in thing in Scala that just says, oh yeah, this is some kind of identifier you can use for the function that will change if the definition of the function is different. That isn't included. But there are things we can do. If you go and poke around in Scala and look at the target directory when you kind of run things and compile things, you might notice that there are all of these little anon functions for .class. So every time you specify an anonymous function in Scala, and also I should say this not valid for 2.12, but or So, but there are things, I'll get to Scala 2.12. But let's just say, at least in Scala 2.10 and 2.11, if you have this anonymous Scala functions, it will make a little class file for each one of them. And those are made of Java bytecode. And you can go and just read that file and hash those bytes, and you will get a pretty decent identifier for the function. So if you go and take this, and then later you change that function so it's like x times 2 to x plus x times 3, that class file is going to change after you compile it. And you can figure out which class file goes to which function at runtime and hash those bytes. And this is also pretty quick. So now that was an easy case. If it's just like x times 2 or x times 3, you just look at the class file for that function, and it changes. But if you have something that is not as trivial as that, there are problems. So you might have a function that depends on some kind of runtime value, and that might be different depending on different runs. And you might also invoke some static method defined on somewhere else. And who knows? And you might also invoke other functions. And what if any of those change? Is the class file for f going to be different if any of those change? And the answer is no. As long as those keep the same name, those things could be changed, or things they depend on could be changed. And the class file for f will have no idea. It'll stay the same. So what you have to do is you have to follow these dependencies recursively until you stop finding things, or only find things you've already seen before, and figure out all the class files that a particular function depends on. Because if any of them change, then that function could easily produce different results. It actually might not. Some of those things could change in ways that it actually doesn't, but there's not really great ways to know that. So the safe thing to do is to assume that if any of them change, that it's logically different. So we want to figure out all of those class files, make a hash of them, and also any kind of runtime values, like say something that comes in at passing in an argument on the command line. You obviously those won't change the bytecode of any class files. And also things like that just happen to be an answer you compute on the fly. If you're using those in your functions, then you obviously have to include those in the hash at runtime. So if we have the ability to generate these logical signatures associated with specific RDDs and such, we're still not done. We need some kind of, we basically specified there's different behavior that might happen depending on whether or not this exists. So we need some kind of mechanism in order to switch these things out. And that is, and that's a tricky question. So how would you do this? Well, you could try to change some things in Spark. There is existing checkpointing mechanisms. They're mostly used for mllib and streaming. I should say the mllib thing is mainly there, and both of those are only really valid within a single execution, and it's mainly there to trim long lineages. They are not valid between different executions. So doing something like this is to make checkpoints valid between different executions. And Spark, how it checkpoints things is it checkpoints things by RDD IDs, which is just an auto increment thing, which you can't really rely on those being the same between different executions. And also there are, for a reason I will get into, there are difficulties when you have definitions that depend on the results of actions. It's kind of getting outside the lazy model, which many Spark things fall into, but not everything. So for that, mainly for that reason, and also because this is perhaps like a kind of an experimental change, I opted to kind of build an abstraction on top of Spark, which does mostly the same thing, except allows you to pattern your things like this. So I made an abstraction called a distributed collection, or a DC. It pretty much does the same thing as RDDs, data frames, and datasets. And in fact, behind the scenes, it's just a dataset. And you can define these, instantiate them without a Spark context, define your whole pipeline, And then at any given point, you can pass in a Spark context to basically get your answer out, to force the computation to actually happen. But until then, everything is lazy. And it has a logical signature. So when your checkpointing is enabled, it can resume from a previously saved thing instead of trying to recompute itself fresh. So when it kind of materializes into getting the actual Spark dataset, RDD, or data frame, it will try to see if there's a previously saved result and use that. So, oh yeah?
When you said you built the distributed collection on top of a data set in RDD.
No, I mean a data set.
But the API is similar.
So, well, I can definitely tell you more after. But basically, the API is very similar between data sets and RDDs, but not completely. But this basically, anything you can call in an RDD and anything you can call in a data set, you can call in a DC. It encompasses both.
So it's like,
And also data frames, but also data sets also encompass data frames. Or data sets encompass data frames. That is, anything you can run on a data frame, you can run on a data set, but not everything you can run on a data set, you can run on a data frame. Well, I guess sort of, because a data set is a row, but it's a little different. So there's not much difference in the API. In fact, as you see, the first 3 lines of this thing are basically the same, except here we basically start with a function defined in the library that kind of holds this thing in a, Spark is like, this will be lazy for Spark. This is also lazy. And this will force, when you call get RDD or get dataset or get data frame for the passing in the Spark context, that's when you could actually just go back to Spark land in order to get your actual thing, in order to save results or kind of force the computation to happen. So it's pretty much like copy-paste code. So that's one of the things I was shooting for, is it should be very easy to try this out. It's just, you might have to change, if you include type signatures, which I'm just doing this for illustrative purposes, you would obviously have to change type signatures where you do that. But it's usually best to write your Spark code in a way where you're not enforcing those, only doing that as necessary. So when you have something like this, you can just toss in a checkpoint, and at a certain midpoint that it will switch in and out depending on what's already saved. So now here's a problem that I kind of alluded to earlier. This only works if we can define things lazily. Here's the thing. This is regular Spark, and if you see this, one of the things we're starting with some numbers, turning them into doubles, taking a sum, and then using that sum in the result, in the definition of our transformation. Say we want these numbers to add up to 1, we can do that by dividing every number by the sum. And the problem with this is this step is not lazy. This will block and execute possibly a large amount of computation. I mean, in this case, not a very large amount. But if you imagine, if you had a large data set and you're doing some kind of sum on it, it might take a while. And the problem there is the definition of this function depends on having this sum, which means if we're trying to hash that, we need to have it before we hash it. And to have it, we have to compute this sum. And that is a problem because we're trying to avoid doing this computation. What do we do? Well, here's another abstraction. Let's call it a deferred result. And it's defined by a function on an RDD, or kind of, basically everywhere in Spark where you would call an action, this is something that is now, instead of returning like a double or kind of some result, it contains like, it's almost like a future, or except it's called a deferred result because it doesn't have it yet. In some ways, I think in Scala Z, it's like a task, although, in fact, with this, so this is also something that can be part of the DAG, the directed acyclic graph that specifies our pipeline. And with this, we can specify entirely lazy pipelines doing whatever we want. So for this example, if we change it so that we want it to be lazy using this abstraction, it looks like this. So basically, the first three things are almost the same, except now, instead of having a double, we have a dr of double. And we can use it in like this. And so this is, instead of doing this as a one step, now it's two steps. So we're basically zipping this with this result in so that we have our original doubles, and then we have this kind of sum that we will have. And then we have like a tuple. So it's the original number and then the sum that's being passed in. So the definition of this function, it doesn't depend on having the sum yet, because we're defining the function so that it is taking in the sum. So we can go ahead and define this function, define all of these steps here, and it doesn't block, it doesn't force the computation, it's defined lazily, which means that we can calculate a signature for any of these, or anything that depends on them, which means that if we checkpointed them or something that depended on them, we could calculate the signature. Calculating the signatures are very inexpensive, goes pretty quick. And then if we had any of them saved already, we could avoid redundant computation and just load from there. So what's the point of all this? The point is we would like to write straightforward, comprehensible pipelines. We want our workflow to be quick and efficient. We don't want to do redundant computation when we're rerunning things and trying to debug our programs, especially if that, it's no big deal to do redundant computation, except when that redundant computation takes a long time. So we would like to save on really expensive redundant computation, but we would also like to avoid writing complicated code. So if we can write things in a concise manner and have systems make them fast for us, that's good. So also, as long as going to the trouble of making abstractions that are switching things out in order to be convenient for us, we can do some other things without really a lot more effort, and maybe a little more effort. We can do things such as automatic failure traps. So as an example, say you define, you have your pipeline and you go and run it, and something comes up where it blows up on one step. And maybe it's only 1 out of 1,000 things that it blows up on, or kind of even rarer than that. What people will generally go and do is say, like, okay, I got some problems. What kind of problem? Maybe the problem is obvious from the message that pops up, but depending on the situation, you might have to do some analysis to see, like, okay, do I only have one kind of problem, or are there a few? Or can I get a better sense of this? And so something that people will often do, if the answer isn't immediately obvious, is to go and select all the items, all the elements that are throwing an exception, and kind of do further analysis on those. And maybe find all the distinct error messages, because you might have more than one kind of exception at a time. So we could do things like, and that's replicating that behavior automatically is not a difficult thing to do. It's basically people generally do about the same thing every time, which is throw a try except, isolate the things that are failing, and then also capture the message so that you could essentially have here's all the things that would fail on this function, and here's the exception they would throw. And you can have some statistics and maybe generate a map of, like, here's the error message to the number of times it occurs with these elements, and maybe distinct on the elements and all that sorts of things. There's a few things like that can just happen every time, instead of us, and it can happen on the actual the execution, one execution, instead of us having to run into problems, write some new code, run that again in order to see the problem. It can also mean that the successful results you can have, if your failures aren't really common, you could have successful things passing through normally, and maybe you encounter several failures at the same time and are able to look at them instead of just encountering the first failure you run into. Generally better, since these things can take a long time to run, to see all of the problems and fix multiple things at once, rather than fixing things one at a time if you have to wait a while to find them. So can you use this? Yes. Is recently open sourced. It requires Spark 2.0. And it's still kind of early. You have to build from source. I'm working on getting it on Spark packages. And it's definitely not, I would say this is alpha. But it's definitely something that if you're building it from source, you can feel free to tweak it. If you're curious to add in automatic behavior of your own, that's definitely something that you should be able to do if you care to do this sort of thing. Now questions?
Are you the sole developer?
There's another developer right here. But it's generally, there's perhaps been 3 contributors in total. It's been used for an internal project at Bloomberg, well, like a couple. And it's generally useful if you are repeatedly running Spark submit to something that might take a while to run.
Do you plan to add support for Python and R?
So the question is, do you plan to add support for Python and R? And the answer is, so currently this is only a Scala library, and this definitely could, a similar thing could be done in Python. The tricky thing is to basically be able to hash Python functions in a way that is consistent. And I would say that for data frames, this is actually a fairly easy thing to do for data frames, except for capturing UDFs. UDFs, you have to do the same kind of thing where you hash functions in the particular language. But for most of data frame operations that don't involve UDFs, it's just a matter of taking the string. There is for any kind of data frame operation, you can grab kind of that column expression. You can grab it as a string, and that string will be unique for the logic, except as it depends on any UDFs. So for data frame things, it's something that's portable between languages, or could be, but I would say not yet for Python and R.
So does it work in Spark Shell or?
It does the same way as any. You could import it into a notebook and use it like that, or in the shell. If you have more questions, we can get to you later. Yes.
Is it possible to make another version of this snapshot function that just replaces your RDD, so you don't have to use this deferred result API?
So the deferred.
In case in my workflow, the only action that I have is just writing results to HDFS.
Oh, okay. So.
I don't recall size, anything like that.
So the question is there a way to just kind of not use this deferred result thing and just make your action happen? And the answer is yes. So the deferred result thing is really for completeness, so that you can specify any arbitrary pipeline. But if you don't need that, you don't have to use it. And so the point of this is to be able to specify everything that's lazy, or be able to specify everything lazily. And if you just want to save your results, the only thing you need to do is whatever kind of result you want, you pass in the Spark context to that DC. You get your RDD or your dataset or your data frame, and you can tell that to save. You're back into Sparkland now, and you can do whatever you want then. So you can save it or anything. The point is that this allows you to specify things in just like lazy, non-blocking. Define all your things, and it'll execute instantly. But when you want to go and do your blocking operations, do your save, you can do that just by passing in a Spark context and doing it. OK. So I think that's time. If anyone has further questions, come talk to me. Thank you, everyone.